In this video, we're going to look at some of the fundamentals of probability. So one of the reasons we need to look at probability is it gives us a basis for making decisions. So let's just look at an example. Suppose it's suspected that at least 45% of people ages 15 to 24 have engaged in unprotected sex. So you've probably heard questions like this before. You would ask a question like this if you were performing a hypothesis test. So for example, you might have the following hypothesis. Since we're trying to prove that at least 45% of people ages 15 to 24 have engaged in unprotected sex, let's let P denote that proportion, and here we would be trying to prove that P is greater than 0.45, and under the null we would set it equal to 0.45. Further, let's say we take a sample of 10 randomly selected individuals and we get the following results. Of those 10 people, none of them have engaged in unprotected sex. So in this particular case, the researcher is likely to fail to reject the null hypothesis because this event is highly unlikely to happen if at least 45% of people have engaged in unprotected sex. So what we're saying here is we suspect more than 45%, but no one in our sample had participated in this particular behavior, so we don't have any reason to actually believe it's at least 45%. Now on the other hand, let's say our sample yielded this result. Notice we've got 5 yeses and 4 nos. So in this case, we found from our sample of 10 that 50% had engaged in the behavior. So the question is this enough evidence to say that in the entire population, which is what P represents, in the entire population, are we finding that more than 45%? And so, is there enough evidence to reject the hypothesis? Maybe, is the answer here. We only took a sample of 10. So, if out of 10 we find 50%, it may be that in the population it's only 40%. So what probability is going to do for us is it's going to give us a way to calculate the probability of observed specified outcomes, assuming that our hypothesized model is correct. So in other words, if in the population, we've got more than 45%, how unlikely is it, or how likely is it to see a sample of 10 come back with 50%? And so that's why we need some probability theory, because it's going to lead up to the idea of hypothesis test, which is where we need to go for statistical inference. So we're going to start out with a little bit of a review of set notation. So in order to discuss probability theory, we need to be familiar with some of those basic concepts of set theory. And we'll denote sets by capital letters. Typically for set theory, we use capital letters towards the beginning of the alphabet. And then we use the lowercase letters to represent the elements. So for example, if we had the set B and B was comprised of 4 elements, we could use lowercase b1 all the way up to lowercase b4 to denote those elements. Some other definitions, the cardinality of a set is the number of elements. So set B that we have up above has 4 elements in it, so its cardinality is equal to 4. We're going to use S to denote the set of all elements under consideration. We're going to call it the universal set. When we move on to talking more about probability, this is what we will use to denote the sample space. So that's why we're using capital S here. All right, we're going to look at some relationships between sets. And so the first one we're going to look at is a subset. So for any 2 sets, A and B, if every point in A is also in B, then we say A is a subset of B, or we could say that A is contained in B. Now, in order to help visualize these, we're going to look at some Venn diagrams. So I've got one here. So we need to first draw a symbol that represents that universal set, or S. And so typically we use a large rectangle to do that. And then here I've got 2 different shapes. I've got a circle and a triangle, and I'm going to use those to denote my sets A and B. So here we're going to let B be the circle and A be the triangle. So notice here that the triangle is contained in the side of the circle. So here we have that A is a subset of B. Notice also B is a subset of S, the universal set, and A is a subset of the universal set. And if we wanted to put some numbers to this to kind of help make it more concrete, we could say that S is equal to 1, 2, 3, and 4. So notice in this case, the universal set has 4 elements. A could be the set only consisting of the number 1. And B could be the set containing 1 and 2. So notice in this particular example, A, which only contains the number 1, is a subset of B, which contains 1 and 2, and B is a subset of the universal set, which contains 1, 2, 3, and 4. So if we wanted to add those numbers to our Venn diagram, we could do it this way. We could put the number 1 inside of the triangle, put the number 2 outside of the triangle but inside of the circle. So notice inside of the circle we do have the numbers 1 and 2, and then 3 and 4 will be outside of the circle but inside of the universal set. The null or the empty set is denoted by this symbol. It is the set consisting of no points. So therefore, the null set or empty set is a subset of every set. Next, we'll look at the union of two sets. So the union of A and B is the set of all points that are in A or B or both. And we denote the union by this right here. So notice the symbol kind of looks like the letter U, so you can think of union there. And so the key word here is or. So when we say A union B, what we mean here is this is or inclusive. So anything in A, anything in B, or anything in both. So again, we'll look at a Venn diagram. So for this particular Venn diagram, again, the rectangle is going to be the universal set. We'll let this circle denote A and this one denote B. So to put some numbers to this time, let's let the universal set be 1, 3, 5, 7, and 9. A is going to be 1, 3. And B is going to contain the elements 3 and 5. So looking here, if we look at all of the elements that are contained in A or B, we can see that A union B is equal to 1, 3, and 5. So we have 3 elements in A union B. If we wanted to add these to our Venn diagram, notice that this piece right here is the overlap between A and B. If we look at our 2 different sets, notice that the element 3 is in both of the sets. So 3 is in the overlap. We see that 1 is in A, but not in B. And 5 is in B, but not in A. And then finally, we have 2 other elements, 7 and 9, which are not in A or B, so I'm just going to place them somewhere outside of those. The intersection of 2 sets, A and B, is the set of all points that are in both A and B. So if we look back up at our previous example, notice that 3 was in both A and B, so 3 would be in the intersection of A and B. We denote the intersection using one of these 2. The first notation is the one that I typically use. And so the key word again here is and, meaning A and B simultaneously. Now if we look at this notation here, let's talk about what this notation means. And we had something similar for the union. When we say A intersect B, what we're saying is that is equal to the set of all x. So that's what this little x here is doing. It's just saying all of the x such that, that's what the vertical line means, X is included in A and X is included in B. Or we could say X is an element of A and X is an element of B. So what the notation does here for us is it gives us a compact way to write a rather long sentence. So in other words, A intersect B is equal to the set of all X such that X is an element of A and X is an element of B. So what we're thinking of here when we look at A and B, we're looking for where the overlap is. In terms of remembering which symbol goes with union and which one goes with intersection, remember that intersection means and this symbol kind of looks like an N, and again, the other symbol looks like a U for union. So again, if we look at our Venn diagram here, if we wanted to draw this out, we could let S again be the universal set, we could have A, and we could have B. This time, let's let S be equal to 2, 4, 6, 8, and 10. We're going to let A be equal to 2, 4. And B be equal to the set having 4 and 6. So in this case, notice the overlap between A and B is 4. So 4 goes in the intersection. If we wanted to draw the rest of it, notice that 6 is in B but not in A. Also notice that 2 is in A but not in B. And then 8 and 10 are in neither. And then if we wanted to fill in the piece of this that represents the intersection, that would be this piece right here. We could have done the same thing up here with the union. If we wanted to shade in the piece that represents the union, that would be everything in A or B, so all of this. All right. We could also talk about the complement. If A is a subset of S, then the complement of A is the set of all points that are in S but not in A. So the complement of A may be denoted by any of these. I should remove this. We don't have a text that has this, but the A bar is the one that I typically use the most. So for example here, again, we're going to let the rectangle represent S. The circle is going to represent A. So let's say that S is equal to 10, 13, 17, and 21. And A is the set containing 10 and 17. So in our picture, we'll have 10 and 17 in here. Outside, we have 13 and 21. So a complement in this case would be everything in S that is not in A. So in this case, we would have 13 and 21 would be the elements of a complement. And then the piece of our Venn diagram that represents the complement, that's going to be everything outside of A. So this yellow shaded bit, that is going to be the complement. Okay. Two sets, A and B, are disjoint or mutually exclusive if the intersection of A and B is equal to the null set. In other words, they have no points in common. So again, our rectangle here is the universal set. We'll let this one be A and this one be B. If S is the set 100, 101, 105, and 107, and A has a single element, which is 100, and B consists of a single element, which is 105, notice there is no overlap between A and B. In other words, the intersection of A and B is equal to the null set. We draw this in our picture. We can see there is no overlap between A and B. And so A and B are disjoint or mutually exclusive. So one thing that you want to start getting comfortable with whenever it comes to reading anything about probability or statistical inference, what you're going to find is there are some things that go by two names. So in this case, disjoint or mutually exclusive. And unfortunately, that's just how things are. So you want to be aware of different terminology that's used. The other thing is different notation. Different texts, different journal articles, they'll use different notation for the same thing. So just keep that in mind. Don't always get set on, well, we're always going to use A and we're always going to use B. Different texts will use different lettering, different symbols, and so I'll try to talk about that as we go through the notes, if there are common things that I see that are different. So an example was up above with the complement. All right. Here's some different operations if you're working with different sets. So these are just some different laws that exist. You can think of these as being very similar to multiplication laws or division laws, addition laws. It's just that these are for sets. So just for example, looking at some of these, notice that A union B is equal to B union A. Well, this makes sense because if A union B is all of the elements that are in A or B, well, that's going to be the same as all the elements that are in B or A. It doesn't really make difference if we switch those. We have associated laws. So notice here, if we add parentheses, that is still going to hold with our unions. Distributive laws. We have De Morgan's laws, which can help us see the relationship between unions and intersections and complements. And then just a couple of useful identities here. All right, so that's just a little bit about set notation. This is going to help us talk about what are called discrete probabilistic models. And so this is where we're going to start talking about the actual probability portion. So an experiment which can be repeated under the same condition and all possible outcomes can be identified is known as a random experiment. For the purposes of this course, when referring to an experiment, we'll assume the experiment is a random experiment. So the sample space is the set of all possible outcomes in a random experiment. So this relates back to that idea of the universal set. It's just now that we're talking about probability, we're going to talk about the sample space. The single outcome or a single outcome of a random experiment is referred to as a sample point or a sample event. And a discrete sample space is one that contains either finite or countable number of distinct sample points. And then an event is a collection of sample points or sample events that is any subset of S. All right, so for example, an adult is to be selected at random and their genotypic sex is recorded. List the outcomes in the sample space. So when talking about the sample space, what we're looking at is all of the possible outcomes that we could find. And so according to the World Health Organization, humans are born with 46 chromosomes. They're in 23 pairs, and the X and Y chromosomes determine a person's sex. So most women are the 46XX, and most men are the 46XY. If you were doing research in this area, though, you would know that there are some individuals that are born with singles. So another option would be 45X or 45Y. And then there are some with 3 or more. And so we could have 47XXX, 47XYY, 47XXY, etc. And so we could put etc. there, or we could do ... So in other words, we want to list all of the possible outcomes. Now those possible outcomes might be determined by the particular experiment you're doing. If your experiment is only concerned with the 46XX and the 46XY, then that would be all that is in your sample space. So another example here, an adult is to be selected at random and the number of permanent erupted teeth is recorded. So again, we're going to list the outcomes in our sample space. There are 32 permanent teeth in the adult mouth. So if we're looking at the number of erupted teeth, it could be possible that that randomly selected person has 0, 1, 2, 3, all the way up to 32. The probability of a simple event is a number between 0 and 1 that indicates the likelihood of that simple event occurring when the experiment is performed. If E is an event, then P of E reads the probability of E. So again, this is some notation that is going to help us take longer sentences and compress it down. So there are three conditions that form the basis of our definition of probability. Suppose that S is a sample space associated with an experiment. To every event A in S, we assign a number. So in other words, the probability of A, P of A, is so the following holds. All probabilities are going to be greater than or equal to 0. There's no such thing as a negative probability of something occurring. The probability of the whole sample space is 1. And then for any sequence of pairwise mutually exclusive events, a similar result holds. So what we're saying here is if we have mutually exclusive events and we look at the probability of their unions, this is going to be equal to the sum of the probabilities. And then here, this result holds for a finite sequence of mutually exclusive events. So here, notice we had ... Here we're just going up to event AN and looking at the sum of those probabilities. And we're going to look at an example in just a moment and talk about, in context, what is happening here. And then just a couple probability rules. All simple event probabilities must lie between 0 and 1. This can actually be proven using axiom 1 and 2. And the probabilities of all simple events within a sample space must sum to 1. And this can be proved using axioms 2 and 3. All right, so let's look at a concrete example here to see what was going on up above. So here's how we could calculate the probability of an event, and this is what's called the sample point method. And so the idea here is we define an experiment and clearly determine how to describe one simple event. We list the simple events associated with the experiment and test each to make certain that it cannot be decomposed. This is going to define our sample space. And then we assign reasonable probabilities to the sample points in S, making certain that all of the probabilities are greater than or equal to 0 and that the sum of all of them together is 1. Define an event of interest, which we could call A or whatever letter you like, which is a collection of sample points, and then find the probability of A. So for example, suppose that we toss 2 fair dice, and we want to calculate the probability of getting a 1 or a 5 on the toss. So here our experiment is we're going to toss 2 dice, and so notice the simple events here are going to be the faces on those 2 dice. Next, we're going to list the simple events associated with the experiment. So this diagram here is that list. So take a moment and confirm here, these are all of the possible outcomes if I roll 2 different die and the faces that they could land on. So make sure, double check here that I'm not missing anything, but I've got that there are 36 different simple events here. In other words, there are 36 different ways that these 2 dice can land. So next, we need to assign reasonable probabilities to those sample points in S. So notice here that there are 36 different combinations. If each of these are equally likely, and if these are fair dice, then they will be, notice that each of these outcomes has a 1 out of 36 chance of occurring. So each of my sample points in this particular case have the same probability of occurring, and that's 1 over 36. That doesn't necessarily always have to be true. So they're all greater than 0. And if each of these has probability 1 over 36, there are 36 different outcomes, then obviously those probabilities add up to 1. Next, we're going to define our event of interest, which is A. So in this case, A is going to be I either see a 1 or a 5 on the toss. So let's look at which elements that is going to consist of. So notice that all of these tosses have a 1. All of these tosses have a 1. All of these tosses have a 5. And all of these tosses have a 5. So everything circled in yellow is a roll that has a 1 or a 5 in the toss. So if we count those up, so we've got 1, 2, 3, 4, 5, 6. I've got another 6 here, which brings me to 12, 15, 18, 20. So looking at these, I have 20 out of 36 that have a 1 or a 5. So if A is the event of getting a 1 or a 5 in a toss, then the probability of A is equal to 20 divided by 36. Okay, so let's look at a couple probability rules. So there are several rules that may be helpful to us when we calculate probability. We're going to look at 3 different ones here. The first one is what we call the additive rule. So the additive probability rule says if I'm looking for the probability of A union B, that's equal to the probability of A plus the probability of B minus the probability of the intersection. So we're not going to give a formal proof of this, but I do want to look at the Venn diagram just to give an idea of why this would be true. So again, let's let the box represent our sample space. We'll let the first circle represent A and the second one B. So let's look at what's going on here. If I look at A, notice A is everything inside of this circle. And if I look at B, everything is inside of this circle. So when I add on the probability of A, I'm looking at, we're looking at everything from this circle. And then for B, everything from this circle. So notice that this middle piece here gets counted twice. It got counted once when I added on A, and it got counted again when I added on B. So this is why we have this subtraction right here. It takes care of the double count because this middle piece, if you'll remember, is A intersection B. We also have what's called the complementation rule. The probability of A complement is equal to 1 minus the probability of A. So if we look here at another Venn diagram, here we could have S, we could have A, and we could have B. So when I look at the probability of A, I have all of A, which is this piece. A complement is going to be everything outside of A. Well, remember that the probability of the sample space is equal to 1. So if I want the blue, I could take 1, which would be the probability of the entire sample space, minus the probability of A, which is the yellow, and that will leave me with the blue. All right, the last thing we've got here is just some methods for counting sample points. So we might need to know how many sample points we have. So the first one is the multiplication rule of counting. So it's what's called the basic counting principle. And it says, if there are n possible outcomes for event E1 and m possible outcomes for event E2, then there are a total of n by m possible outcomes for the series of events E1 followed by E2. And this can hold true for more than just 2 events. So, for example, suppose you like to mix and match your outfits. For today, you have selected 2 shirts, 3 pairs of pants, 2 belts, and 5 pairs of shoes, all of which match. Now you need to decide which shirt, pair of pants, belts, and pairs of shoes you want to wear. How many choices do you have? So in other words, how many outfits could you find here? Well, if we think of it in terms of kind of a chart here, for shirts, you have 2 options. So you could have shirt 1 or shirt 2. For pants, you have 3 pairs of pants, so you could have pant 1, pant 2, pant 3. For belts, you got 2 belts, so belt 1, belt 2. And then for shoes, you've got 5 different shoes. So it doesn't look like there's a whole lot of combinations here, but one way to think of this and to kind of thinking about how these would be counted, let's say we just start out with shirt 1. So notice for shirt 1, we could go shirt 1, pant 1, belt 1, shoe 1. Then we could go shirt 1, pant 1, belt 1, shoe 2. And I could keep on going. And then I could do the same thing if I went from shirt 1, pant 2, belt 1, and then go through all the shoes. And I could keep on finding all of these combinations. So what ends up happening is for shirts, you have 2 options. That gets multiplied by the 3 options for the pants, multiplied by the 2 options for the belts, multiplied by the 5 options for the shoes, and it ends up there are 60 different outfits in this particular case. There are also counting rules for permutations. So this is going to be the number of ways to arrange an order in distinct objects, taking them R at a time. Where n and r are whole numbers, and n has to be greater than r. The big thing here is that order matters. Right, and just as a reminder, in case it's been a while, if you have n factorial is equal to n times n minus 1 times n minus 2, all the way down until you get to 2 times 1. And then just some other facts that are useful. N factorial is equal to n times n minus 1 factorial. And 0 factorial is equal to 1. Alright, an honor society has 20 members. The society needs to select 4 officers: president, vice president, secretary, and treasurer. How many different slates of officers are possible? So notice here we've got 20 different people. We're going to select 4 of them. The order in which we select the 4 different people matters because that order is going to tell us who's president, vice president, secretary, and treasurer. So in other words, what we're saying here is we have 20 people and we need a permutation of 4. So to find this, what we can do is we can use our formula we have up here. Notice that the 20 is the n and the 4 is the r. So we have 20 factorial divided by 20 minus 4 factorial, which is equal to 20 factorial divided by 16 factorial. If you expand this out, notice that 20 factorial is equal to 20 times 19 times 18 times 17 times 16 factorial. And the reason that is true is I could keep on going and have 16 times 15 times 14 times 13 all the way down to 1, but that whole chunk is just equal to 16 factorial. And I stop there because I've got 16 factorial in the denominator. So notice that those two are going to cancel. So this is going to be equal to 20 times 19 times 18 times 17. And this is equal to 116,280. So this is one of the really interesting things about counting. If you were initially said, hey, there's 20 people, and we need to figure out the different ways that we could select 4 of them, and those 4 people be assigned to president, vice president, secretary, and treasurer, you probably wouldn't initially think that, the options or the ways that that could be done is greater than 100,000. All right, we've got one last example here. This is going to be counting for combinations. So the difference between a combination and a permutation is, in this case, order doesn't matter. And this is going to become important later on when we talk about the binomial distribution. So kind of keep this in the back of your mind. So the number of combinations that n objects can take r at a time is what we call n choose r. And you'll notice that the formula is very similar to the permutations, but the difference is this piece right here. So that r factorial in the denominator, that's what's going to get rid of the order. So if we go back up to our permutation, remember our example said an honor society has 20 members. We were going to select 4 people, and we needed to select them in order because we needed to assign president, vice president, secretary, and treasurer. Well, what we're saying in combinations, we could use this same example, but instead of selecting those 4 officers, maybe we just want to select a subcommittee of 4. And so there is no ordering within that subcommittee. We're just choosing 4 different people to be in the subcommittee. And so that would be an example where order doesn't matter, and we would be looking at a combination and not a permutation. So for example, you want to select 3 students from your student organization to represent you at the National Convention. There are 8 students willing to attend the convention. How many groups of 3 are there? So notice we've got 8 people in total. We're going to select 3 of them. The order of those 3 doesn't matter because they all have equal standing, so this would be a combination problem. And so what we're saying here is we have 8 people, we need to choose 3 of them. So using the formula here, we're going to have 8 factorial. N is always our total number, which is 8, divided by 3 factorial times 8 minus 3 factorial. And this is equal to 56. So there are 56 different combinations here. If the combinations here were new to you, don't worry too much about these 3 rules. The one that's going to end up being the most important, again, is this one. And so we're going to come back to this when we look at the binomial distribution. So just keep this one in mind for later on.